A1 up through A sub p are integers. That's going to be the ring that we're interested in. So if I take two things of that form and add them together, I claim they get something of that form. This is closed under addition. Do you believe that? If you take two things, A1 plus A2z and so on, and then I take B1 plus B2z and so on, I add them together, the first coefficient is A1 plus A2, and so on. So we add them, two of them together, we're cool, right? That stays within the ring. Okay, what if I multiply them together? That's a little more complicated. But I claim that if you multiply two of them together, it's still in that form, because once you get to z to the p or higher, z to the p, remember, is 1, z to the p plus 1 is z, and so on. So I claim you still get something of this form. This is still a ring. This is what we're going to use for fully homomorphic encryption. So the fully homomorphic part comes from the fact that this is a ring. It's closed under addition and multiplication. The security, the privacy aspects of fully homomorphic encryption are going to come from its structure as a lattice. And I'll say in a minute what I mean by lattice. So what we're going to do is, to turn this into a lattice, you're going to take something of this form, so something in our ring, and you're going to strip off the z's, and you're just going to look at this lattice vector in p-dimensional space. So this is going to be a p-tuple of integers. So remember, the AIs are integers. You're going to look at a p-tuple of integers. This is going to be a point in p-dimensional space. Now, so there's a lattice. That's what I think of as a lattice. So a lattice is, you have your apple pie with the lattice work, crust. That's a lattice. This is a lattice. So in cryptography, you're dealing with very high dimensional lattices. Now, I can't draw a high dimensional lattice, so I'm going to give you a two-dimensional lattice just for simplicity. But really, in practice, you're going to have a very high dimensional lattice. So what we have here, all these dots, these are the lattice points. Okay, so I'm going to try to give you just a taste for how to do the mathematics in fully homomorphic encryption. Okay, so Bob is going to have a private key and a public key. His private key is going to be a good basis for the lattice. What do I mean by a basis for the lattice? And then what do I mean by good? Okay, basis for the lattice. So his private key is going to be two of these lattice points. The one over here and the one over here, okay? This one and this one, the ones being pointed at. So why are they a basis? I claim that you can get any lattice point in that picture by taking multiples of one of those points and adding to it multiples of the other point. So for example, if I take twice this point, I get this. If I take 3 times this point, I get this point. And twice this point is here. If I add this point to this point, I get this point, and so on. And I claim by taking multiples of this, integer multiples of this, and integer multiples of this, I get all of the lattice points. That's what it means to be a basis of the lattice. What does it mean to be good? It means that these vectors, so we have one vector here, one vector over here, these vectors are nearly perpendicular. They're nearly orthogonal. So that's a good basis. Okay, so that's Bob's private key. Bob's public key is going to be a bad basis for that same lattice. So we have the same lattice here, and we have a different basis. So if I take this point and this point, I claim if you take multiples of one point and add to it multiples of that other point, you generate the whole lattice. You can get the entire lattice that way. What makes this a bad basis? It's very skewed. These vectors, this vector and this vector, are not very perpendicular to each other. So this is a bad basis for the lattice, and that's what's going to be the public key. Everyone is going to know Bob's public key, but only Bob knows his private key. Okay, so how are we going to encrypt and decrypt? So every point in the space, by which I mean not just the lattice points, but every point in this space, every point in this two-dimensional space, there's a unique way. So if we take any point at all, I can translate it to what's called the fundamental region. So my fundamental region is going to be the interior of this parallelogram. Any point, you can add to it a lattice point that'll put it inside this parallelogram, I claim. And in fact, what I want to do is translate this parallelogram so it's centered at the origin and make that my fundamental region. Let's see, I think I fill it in there. So the filled in area is going to be my fundamental region, and I claim that any point, you can find a lattice point that you can add to your point to get inside this region. That's what makes it fundamental. So you should think that through as an exercise, is try to figure out why that's true.